Hello all, I am Ankita Tondwalkar. I recently defended my PhD in Electrical and Computer Engineering at Rochester Institute of Technology, Rochester, New York. My research lies at the intersection of wireless communications and artificial intelligence machine learning. I'm very glad that my research is one of the contenders for the Women in 6G Best Research Paper Award. I would like to talk about the motivation of our work before I move on to the contributions. The rapid growth in wireless communications and services has motivated efficient spectrum access, spectrum allocation, and spectrum utilization. Dynamic spectrum access enabled by cognitive radios allow for intelligent and adaptive spectrum resource utilization. Most practical wireless networks operate in dynamic and non-stationary environment, and therefore we emphasize on uncoordinated and distributed multi-agent cognitive radio network operation, which more accurately reflects a practical wireless network deployment. In uncoordinated and distributed multi-agent cognitive radio operation, the cognitive radios learn independently to take the best decision for resource allocation, resulting in a non-stationary environment. This non-stationarity makes resource allocation fundamentally challenging, and therefore our work employs model-free reinforcement learning to address this challenge. My first paper focuses on applying deep Q learning for resource allocation under the challenges of a non-stationary environment, and my second paper focuses on the application of proximal policy optimization for addressing the resource allocation under the same challenges of non-stationary environment. I will now list down the contributions of our first work followed by the second. For our first work, our work is the first to present undistributed and distributed and uncoordinated multi-agent deep Q learning algorithm in the non-stationary environment. We analytically prove convergence to equilibrium policies in most of 99% cases when the learning time is arbitrarily long. Our DQL algorithm learns faster, requires less than half number of training steps than the table-based approach in a non-stationary environment. As an additional contribution, we also show that a standard single agent deep Q learning may not converge to optimal policy or any policy because of the large variance in the Q value estimation arising out of non-stationary environment. In our second paper, our work is the first to present multi-agent proximal policy optimization under the challenging case of non-stationary environment for the application use case of cognitive radio networks. The PPO algorithm requires less than 70% training steps compared to the table-based approach, and about 25% less training steps compared to the DQL approach, and learns faster. The impact of our research is in the sense that we aim for faster and accelerated learning under the challenges of a non-stationary environment, and therefore our research finds applications in heterogeneous 5G and 6G networks, military and emergency communication services, unlicensed spectrum sharing, as well as dense IoT deployments. I believe our work deserves to be rewarded because we address the fundamental challenge in a non-stationary environment in wireless communications, which is efficient resource allocation in non-stationary wireless communications. Our work addresses real-world spectrum scarcity problem by providing a scalable and autonomous solution in order to enable 5G, beyond 5G and 6G networks, as well as future intelligent wireless networks. Thank you.